Okay, so our last lesson this year is going to be just kind of touching on the basics of trigonometry. Not a lot of in-depth stuff, just some of the basics of trigonometry. And we're going to define these three primary functions of sine, cosine, and tangent to be the opposite over the hypotenuse, the adjacent over the hypotenuse, and the opposite over the adjacent. Let's say that again. In a triangle, we're going to define the sine as being the opposite leg divided by the hypotenuse, the length of. The cosine as being the adjacent leg divided by the hypotenuse. And the tangent as being the opposite leg divided by the adjacent leg. Some people remember that by saying some old horse, sine is opposite. Whoops, what happened there? Go back up here. Sine is opposite over the hypotenuse. Cosine is adjacent over the hypotenuse, and tangent is opposite over the adjacent. Some people remember that. Some old horse caught another horse, taking our apples. Let's look at an example here. We know that the sine is the opposite leg divided by the hypotenuse. In a right triangle, so that's the hypotenuse, that's easy, it's the slanted one. Which side is on the opposite side of that angle? Well, that would be A. That's the opposite. And of course, adjacent means next to, so B would be the adjacent leg. And the sine then would be A over C. The cosine would be the adjacent over the hypotenuse, so the cosine would be B over C. And finally, the tangent, which is the opposite over the adjacent, the tangent would be the opposite over the adjacent. It would be A over B. Let's look at another example. The sine is the opposite over the hypotenuse, and for this angle, that's the opposite. And that's easily the hypotenuse. So this must be the adjacent. And if the sine is the opposite over the hypotenuse, then the sine is 1 over 9. If the cosine is the adjacent over the hypotenuse, then the cosine is the square root of 80 over 9. And the tangent would be the opposite over the adjacent, so it would be 1 divided by the square root of 80. And for this class, you can leave that alone. You don't need to rationalize or simplify your radicals. All right, so now let's use the Pythagorean theorem, which I'll remember from high school. That says that the square on the two legs equals the square on the hypotenuse. Pythagoras didn't know a squared, b squared, c squared. He was Greek. He says that this square plus this square equals this square. That's what he actually said, or actually proved, or his institution actually proved that. Okay, so we don't know what this one is. I'm going to call it x. And I know that the first leg squared plus the second leg squared equals the hypotenuse squared. It may be easier if I write that backwards, if I start with the hypotenuse squared, because the hypotenuse is the one that's usually the easiest to identify. That square equals the other squares added together. Now, if you need to use your calculator, look it up, but 289, 225, solving the equation, x squared, swinging that over, change the sign, add a negative 225 to both sides. X squared equals 64. So algebraically, x would be either positive or negative 8, but since we're talking about lengths, I'm going to say that x is 8. All right. The hypotenuse, opposite, adjacent. For this angle right here, that's the opposite. That's the adjacent. So the sine then would be the opposite over the hypotenuse. The cosine is going to be the adjacent over the hypotenuse. And after you do this 3 or 4 times, you'll realize that the tangent is always, just cancel those 17s out, 8 over 15. It is the opposite over the adjacent, but if you just cancel the 17s out, the denominator's out, you get the rest. Okay, let's look at this one. All right, so the hypotenuse, which is x, equals one leg squared plus the other leg squared. Getting my calculator out, 144 plus 36. Getting my calculator out, that's 180, which is not a nice square root. So we're just going to say x is algebraically positive or negative square root of 180. But since we're talking about lengths, we're going to say the square root of 180. So for that angle, the sine is the opposite, and the opposite side on that angle would be 12 over the hypotenuse. The adjacent would be 6 over the hypotenuse, and the tangent would be the opposite over the adjacent, 12 over 6, or just plain 2. Either way is fine. That's about all there is to trigonometry. We could just use some more applications of that. Let's look at this. The sine is 2/3. I've given you the value that the sine is 2/3. Well, the sine is the opposite, which is which letter or number? For angle B, which is the opposite side? It is P. Over the hypotenuse, which is 6, and cross multiplying, 3P equals 12, P equals 4. So P is 4. Now, how am I going to find Q? I'm going to go back and use the Pythagorean theorem. The hypotenuse squared equals one leg squared plus the other leg squared. The hypotenuse squared equals one leg squared plus the other leg squared, which says 36 is 24 plus Q squared, or Q squared is, subtracting 24 from both sides, 12. So Q would be the square root of 12. Algebraically, the positive or negative square root, but in terms of length, the square root of 12. All right, the tangent is 1/4, and the tangent is the opposite over the adjacent, and P is the hypotenuse. So the opposite is going to be Q. The adjacent is going to be 8. And using that equation, since I knew the tangent was 1/4, I know that Q over 8 is going to divide down and reduce to 1/4. So 4Q equals 8. Q is 2. And from Pythagoras, I know that the hypotenuse squared equals a leg squared plus a leg squared. So the hypotenuse squared equals a leg squared plus a leg squared, which is 64 plus 4, which is 68. Not a nice even square root, so P is the square root of 68. So finally, the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And what did you tell me Q was? Square root of 12? And you can't simplify that up. That's not a 12, that's a square root of 12, which is 3 point something. And the tangent is the opposite over the adjacent. The opposite over the adjacent, which is 4 divided by the square root of 12. Or looking here, if you cancel the 6's out. All right, so I have an 8, a 2, and we calculated Q to be the square root of 68. The sine is the opposite over the hypotenuse, which is 2 over the square root of 68. The cosine is the adjacent over the hypotenuse, which is going to be 8 over the square root of 68. And just looking at this picture, if you cancel the square root of 8's out, you get 2 over 8, square root of 68, or 1/4. And from our definition, the tangent is the opposite over the adjacent. The opposite over the adjacent, I get the same thing. All right. The last step before we review. If A is 3, the square is 9. If C is 5, the square is 25. And if these two squares have to equal that square, that means that this square is 16, so the length is 4. That's what we call a Pythagorean triple, a set of whole numbers that fit the a squared plus b squared equals c squared pattern. Let's try another one. If the side is 5, the square is 25. If the side is 12, the square is 144. And I don't know how big that square is, but I know that the leg squared plus the leg squared equals the hypotenuse squared. And these two together make 169. So if the square is 169, that means the side is 13. That's another Pythagorean triple. You might want to put those in your notes. You're going to need those for later on. Okay, I have a square plus a square equals a square, and using my calculator, that is 576, and that is 625. Using my calculator, subtracting that, I get 49. Well, if 49 is the square, how big's the side? The side is 7. There's another Pythagorean triple. Finally, if a side is 8, the square is 64. If a side is 15, get your calculator out, 225. And I don't know how big that square is, but I know that those two squares have to add up to that square, which get my calculator says 289. And again, using your calculator, if the square is 289, the side is 17. There's a fourth Pythagorean triple that we're going to use. Okay, so let's see if we can't find some way to identify all of these as one of those Pythagorean triple multiples. Will you agree that if I take the 50 over the 130, that reduces down to a 5 space 13? The 50 and the 130 reduces down to a 5 and a 13. Which Pythagorean triple over here matches a 5 at the first and a 13 at the end? Which Pythagorean triple matches a 5 at the beginning and a 13 at the end? Well, that's the green one. So if it's 5 and 13, it means that needs to be 12. The triple is 5, 12, 13. Now, how did I get a 50 and a 130? From the 5 and the 13 times 10. So this is going to be 12 times 10, which is 120. Let's look again. We've got these 4 Pythagorean triples over here. We have these 4 Pythagorean triples over here. And I recognize that a 50 and a 130 can be reduced down, take out a common factor, to 5 and 13. And I see that this is a 5 and a 13 multiple, so that one's got to be 12 to make it be a Pythagorean triple. So this is 10 times 5 and 10 times 13. This must be 10 times 12. Let's try another one, see if that gets a little clearer. Looking at this, I think I can divide a 2 into both of those, And if I divide a 2 into both of those, I get an 8 and a 15 and a blank. Well, sorry, I forgot this. 5, 12, 13. All right, which Pythagorean triple starts with an 8 and a 15? The purple one down here. That means this would have to be 17 to be a triple. So my triple is 8, 15. That's my base triple, 17. And I recognize in each case that A, B, and C is just 2 times my triple. So that would have to be 34. Now this next one's harder to see, and I wouldn't give you one like this on a test. But if you recognize these two with a 0.7 and a 2.5, you might say, well, it's just this one divided by 10. It is 7 and 25 divided by 10, so my middle is going to be 24. My Pythagorean triple, my base Pythagorean triple is 7, 24, and 25. These are just one decimal in those divided by 10, so B is going to be 2.4. This one's a little harder to see, but you might recognize that 6 and 6.5, if I double them, are 12 and a 13. Do you see a Pythagorean triple that has a 12 and a 13 on the far end? Well, this one right here does, doesn't it? This one right here does, doesn't it? So this would have to be 5 to complete the Pythagorean triple. And the number on top is just half of the one below it, so this would be 2.5 in a 5, 12, 13 triple. Let's skip this last one. It's got the decimals in it. I don't want to do it. All right. The last new thing. The cosine is 3/5. Now, I don't know what the numbers are. I know they reduce down to 3/5. So let's just use 3 and a 5. If I have a triangle here, and I say this angle's right here, where would the 3 go and where would the 5 go if the cosine is 3/5? Well, looking back on your notes, the cosine is the opposite over the adjacent, it is the adjacent over the hypotenuse. The adjacent over the hypotenuse. Okay, so for this angle, where's the hypotenuse? Well, the hypotenuse is right there, which is the opposite side from that angle over here. That means that must be the adjacent. So the 3 and the 5 are going to go here and here. Now, from Pythagoras, the hypotenuse squared equals the side squares. I'm going to call this one x because I don't know what it is. Solving that equation by adding a -9 to both sides. X is positive or negative 4, but in terms of lengths, x is 4. So the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse, and that was already given to you. And the tangent is the opposite over the adjacent. Let's do another one. The tangent is 3/5. And what is the tangent? The tangent is the opposite over the adjacent. So for that angle, the opposite is 3 and the adjacent is 5. And I'm going to call that one x. Now I've got the same numbers, 3 and 5, but they're positioned differently. Remember, Pythagoras tells me that the hypotenuse squared equals the other squares added together. And since x squared is not a nice square root, it's an irrational number, we're going to say it's just the square root of 34. So the sine, which is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, And the tangent is the opposite over the adjacent. Let's do one more. The sine is 2/5. And we know that the sine is the opposite over the hypotenuse. And Pythagoras tells me that the hypotenuse squared equals the other two squares added together, that the hypotenuse's square equals the other two squares added together. And since 21 doesn't have a nice square root, we're going to say it's the square root of 21. Once again, the sine is the opposite over the hypotenuse, which is given. The cosine is the adjacent. Oh, that should be 21, not 25. Over the hypotenuse. And the tangent should be the opposite over the adjacent. For angle B, 2 is the hypotenuse, x is the opposite. That means that 1 is the adjacent. And Pythagoras tells me that the hypotenuse squared equals a leg squared plus a leg squared so x is positive or negative square root of 3, but in terms of lengths, we're going to just say it's the square root of 3. So the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. The problem tells me that the cosine is 1/2, and the cosine is the adjacent over the hypotenuse. So the adjacent is 6 over the hypotenuse, which is y, equals 1/2. Cross multiplying and solve the equation, you get 12 equals y. Y is 12. Now from Pythagoras, I know that the hypotenuse squared equals a leg squared plus a leg squared, using my calculator. Oops. And 108 is not a nice easy square root, so it's going to be the square root of 108. Almost finished. Almost finished. Let's draw a picture. Probably on your test you might see something like this. You might just see a triangle already drawn for you, and the letters A, B, and C, and ask you what A equals, what B equals, and what C equals. So for this angle, the sine is the opposite over the hypotenuse, and that's clearly the hypotenuse. So that means A would be the opposite side from that angle, and B would be the adjacent side. And I know that the sine is 2/5, so A equals, the sine is 5/12. A is going to be 5. C is going to be 12. And from Pythagoras, 12 squared equals 5 squared plus B squared. Which is B squared is 119, which doesn't have a nice square root. So B is the square root of 119. That's probably as far as I'm going to ask you to go. What is A? What is B? What is C? Because it's hard to enter square roots. But the sine would be 5/12. That was given. The cosine would be the square root of 119/12. And from these two, the tangent is 5 over the square root of 119. All right, looking back at our Pythagorean triples, if you factor this down, you'll realize this is 3 times 15, and this is 3 times 17. And what Pythagorean triple starts with a 15 and a 17? The one that starts with an 8. The one that starts with an 8. So my base triple is 8, 15, and 17. And this is 3 times 17. This is 3 times 15. This better be 3 times 8. I don't know what that X is for over there. All right, I'm going to put this on the canvas, and good luck to y'all. And this will be the last thing we're going to cover before your exam. Good luck, and I miss seeing y'all.